Okay, let's try to start.
Okay, so I'm gonna mute myself.
Amir is going out. Okay, no problem. I think he will connect to us. Today I plan to discuss two equations which lays in the base of the turbomachinery. So our next lecture will be at the Monday at morning, as far as I remember, at 11:30. So I suggest I have some business at the morning and I could late. That's why I suggest to have lecture together with the French guys like 1 week, like 2 weeks ago. So,
yes, it's okay.
I think especially for you because it's you see some guys in the Skype
Attending.
yes. You are not alone. So that's why today I plan to discuss two equations. The French guys study approximately the same things. That's why maybe if nothing will be changed, at Monday we will make lecture together with the French guys in 15:15. So, okay, let's start. Let's not will be wait other guys. Let's try to study fast. So I will share the screen. Do you see the screen?
Yes.
Perfect. So today we will discuss two equations, two formulas, which I don't know, you are not start from the first course in our university, but your classmates must to study gas dynamic and thermodynamic lectures. In any case, as far as I know, Professor Dima Uglanov read lectures in gas dynamic. These two equations, two laws you must to study in gas dynamic. From first hand, I want to refresh the information about these equations because it's really very important for any industrial application deal with the gas dynamic, deal with the fluid flows. It's the first moment. And the second moment, of course, we will apply this equation to the turbomachinery and we will find some important conclusion. So let's start from the continuity equation. So let's study the flow through any channel. In reality, at this moment, it could be any channel if you want, but of course we will look to the turbomachinery, but it's not important at this moment. So at this picture, you will see the axial turbine. Let's imagine what we know everything about the flow in the inlet of the channel and at the outlet of the channel. So we know velocity, density, pressure, cross-section area, any parameters which we need, we think what we know. It's the first moment. The second moment, let's split our flow to the great number of the small tubes. So here on the picture you will see example of such tube. Of course, this tube which are drawn on the picture is rather big. in reality, the flow tube which we will take will have very small cross-section area. Such small cross-section area, what we could to think what the parameters along the cross-section area in the direction normal to the velocity doesn't change. It could be think what it's uniform. And of course, we are not taking account leakages and our flow from the backside. By other words, the flows comes into the tubes through this section and comes out through this section. We have no any additional flow supplying or extracting from the backside. So, okay, let's study the flow through one small tube. At the first time period, I will try to, sorry. At the first time period t0, the tube was in the position 1, 3. So the tube was at this position. After very small time period dt, which leads to 0, of course, the tube will be moved to the position 3, 2. So at this moment, it was in the position 1, 4. After the small time period dt, it's moved to the position 3, 2. The time period dt is too small, what we could to say what the parameters in the section 1, 3 are equal. So the time period so small, what the parameters between the section 1 and 3 and 4 and 2 doesn't change. It's very small time period. So if we look carefully to this flow structure, we could to find very interesting moment. The position 3, 4 doesn't change. So we could to imagine what we have worm 3, 2. So let's draw some funny worm. So at first period, worm take the mass 1, 3 from inlet position, and after time dt, it's the at position t0. So it's take this volume inside, and after time t plus dt, at time period t plus dt, it's drop volume for sorry, it must be for 2. So it's, by other word, we could to represent this flow like the flow through the tube. We have a non-moving, non-changing tube 3, 4, and at first moment we are supplying some volume of fluid inside the tube, and after at the same period of the time, other volume of the fluid comes out from the opposite side of the tube. So of course you are imagine what the mass of the fluid which comes inside the tube are equal to the mass of the fluid which comes out through the tubes. That's why we could to write what the mass of this volume, mass of volume 1, 3, equal to the mass of the volume 4, 2. the mass which comes inside the tube are equal to the mass which comes out from the tube. By other words, it's the mass conservation law. So let's erase this picture. Okay, let's calculate the mass. Let's calculate the mass of the fluid which comes inside our small tube. How to calculate it? Very easy. Mass could be calculated like density multiplying to the volume of this mass. Density of the fluid multiplying to the volume of this mass. About the density we are discussed what we know all parameters. That's why we think what we are know density. How to calculate volume? Very easy. Volume could be calculated. In reality, it's the cylindrical volume. And volume could be calculated like height of the volume. Let's use letter H. Multiplying to the cross-section area, to dF. And the next question, how to calculate height of the volume. It's very easy because we know velocity and we know time period. We could to say what the section number 1 comes the distance which are equal velocity multiplying to the time. That's why this relationship velocity multiplying to the time, it's the height of the volume. We are multiplying it to the cross-section area of the volume, and we are receive volume of the mass, and we are multiplying it to the density, and finally we are receive the mass of the volume. It's very easy. So, and the same for the outflow. So, of course, because the mass which comes in equal to the mass which comes out, we could to make equal these two equation, and we are divide all parts of the equation to the time, to the dt. Mass divided to the time, it's the mass flow rate. That's why we are changing the designation to dg, because we are use letter g to designate mass flow rate in our equation. So, and after that we are assume all our small tubes, we are integrate our flow, and finally we are receive such equation. Of course, we need to if you will make integration, if you are realize this equation, you are find what final equation will have only density, cross-section area, and velocity. But let's imagine what we could to have supplying of additional mass or extracting some mass from our process. That's why we need to add possible supplying or possible leakages of the flow from our channel. So, and finally we are receive such equation which are called continuity equation. It's really very important equation. It's really very widely used in different area of industries. Of course, you could do not. So, of course, you could do not work with turbomachinery in the future. Of course, you could do have no job in the area of the gas turbine engine. But if you will work as engineer, you could use this equation in any range, in any industry. For example, let's imagine you need to calculate the sizes of the tube which are supplying the room at which you are located right now for designing of conditionary system. So you need to find, let's try to draw. You have the room, you are located inside, and you want to find what the sizes must have the tubes which will supply the fresh air in your room. How to calculate it? Very simple, using this equation. First, of course, you know the density because we know the parameters of atmospheric air. Uh, we need to find mass flow rate. Typical requirement for the rooms to change the volume of the air not less than 8 times. So if you know the volume of the room, you could do could you switch off the
عامل
sorry,
ميوت انا
one second. So such better. Let's return back to the presentation. So do you see the presentation?
Yes.
Perfect, Sofia, perfect. So I will lost it. So we are discuss the application of the continuity equation. So I try to explain the example of using this equation in the industry. So, for example, you want to calculate the sizes of the tube which are supplying the fresh air to the room at which you are located. How to realize it? Using this equation. So, you know the density of the atmospheric air. You could to calculate mass flow rate because we special building requirements of which says, for example, what in education rooms the fresh air must be replaced not less than 8 times per hour. That's why if you know the volume, if you know density, you could to calculate the minimum mass flow rate which need to provide your conditionary system. And after that, you are choosing this velocity. This velocity are choosing from experience. For example, if we are speaking about the conditionary system, this velocity must be lower than 4 meters per second. The problem will be in the noises. Of course, you could to use higher speed, but you will achieve additional hydraulical losses. But I think you need to have rather big speed to achieve huge losses. But other problem, what if the velocity of the air will be very fast, you are receive noises. Of course, it's not comfortable in our houses. So, and after that, based to this equation, you will find the cross-section area, like mass flow rate divided by density and divided by velocity, and based to the cross-section area you will find the nearest sizes of the tubes. It could be round tubes, it could be square tubes, it depends from your case. It's the first example. The second example, very typical for the oil industry. For example, you are working in the company which designs some equipment for the oil industry. And typical task we need to find the diameter of the tube which supply some oil equipment. Usually we know mass flow rate of the oil. Usually we know density. We take the velocity of the oil by experience. For the oil, typical velocity approximately 10 meters per second to avoid high hydraulical losses. And using the same equation, we find cross-section area. And finally, we could, based to the value of cross-section area, find the tubes which we need to use for our oil system. So it's a simple example from the different area of industries, and I think you see what these equations are very useful and could be used not only in gas turbine engines, not only in the turbomachinery. So, and I pay your attention to this moment. The mass flow rate could be calculated using continuity equation by multiplying density, cross-section area, and velocity. It's very important to understand what the mass flow rate are determined by velocity which are normal to the flow surface. What it means? For example, you have the wall and you have the hole in the wall. The cross-section area and the flow comes to the hole with the velocity c and flow angle alpha relative the wall surface. The surface of the flow, which are determinate mass flow rate through the hole, it's the surface of the which are normal to the x of the flow. Of the hole. And for the calculating of the mass flow rate, you will need to use this equation. So you are calculating density, you're multiplying density to the cross-section area F1, it's mean cross-section area of this hole, and multiplying to the velocity normal to the cross-section area. It's mean normal to the direction of this cross-section. And it's mean what you need to use projection Cn to calculate it. So it's very important what the mass flow rate are determined by projection of velocity normal to the flow surface. Why it's important? Because in the turbomachinery usually flows comes inside or comes out not in normal direction. Usually we have some angle between the flow surface and the flow direction, and that's why it's need to keep this information at your head, because it's important for calculating of parameters. So, for example, if we are speak about the Excel turbomachinery, I refresh information for you. What the turbomachinery could be Excel, then you have the x of rotation, and the direction of the flow approximately correspond to the direction of the x of rotation. At this case, mass flow rate will be determined by axial projection of the velocity, because this projection normal to the flow surface in the inlet and at the outlet. The same at the outlet, CA. In any case, in axial turbomachinery, the mass flow rate are determined by axial projections of velocity. If we will speak about the centrifugal compressor, I refresh the information for you. What the centrifugal compressor, it's the type of the compressor at which air comes in axial direction, approximately parallel to the direction of x of rotation, and it's come at lower radius, and then in rotor wheel it's changed the direction and comes out in radial direction at the upper radius. It's the centrifugal compressor. And if we will speak about the centrifugal compressor, the mass flow rate through the inlet section are determined by axial projection because it's normal to the flow surface. And at the outlet, flow surface will be the annular surface, and normal direction here will be in radial direction, so it will be at this direction. That's why mass flow rate through the outlet section of the centrifugal compressor are determined by radial projection of the velocity. If we will speak about the centripetal turbine, in centripetal turbine we have the opposite direction of the flow. In centripetal turbine, the air comes in at upper radius in radial direction and comes out at axial direction at lower radius. So at this case we have the opposite picture relative the centrifugal compressor. So in the inlet section we will have radial velocity like radial projection of velocity will determine the flow, mass flow rate, and at the outlet mass flow rate will be determined by axial projection. So I think that's all about this slide. So this information, I hope you are already studying with the Professor Dima Uglanov. I hope you are remember it, and I hope you understand it. And I refresh this information for you because it's really important, because it's very widely used in real engineering practice in many industries. But of course, for us, it's much interesting to apply this equation to the turbomachinery. So let's apply this equation to the turbomachinery. And 1 second. So let's imagine we have some turbomachinery. At this moment, it's not important what kind of the turbomachinery. We have some flow comes, we have some flows which comes out. Let's write the continuity equation to the turbomachinery. Mass flow rate through the first section equal to the mass flow rate through the second section. And we could to write what the mass flow rate through the first section, it's the density multiplying to the normal velocity at this first section and multiplying to the cross-section area F1. And this mass flow rate equal to the multiplying of parameters at the outlet of the turbomachinery. So, and finally, we need to a little bit change this equation to this shape. We will extract a relationship between the cross-section areas. It will be like here. C1, C1n. So let's study this equation and let's apply this equation to the turbomachinery flow. Before we will start, we will make the assumption what the normal velocity is approximately equal at the inlet and at the outlet. It means what we could do avoid these two elements from our equation. Of course, you could to say in real turbomachinery the normal projection of the velocity could be not equal. But in reality, it's the typical design and practice what normal velocity in the inlet and at the outlet of the stage of the turbomachinery will take equal. It's really typical design and practice. It's the first case. And at the second case, you see what to the mass flow rate we have influence of density and velocity. If we will speak about the compressor, for example, in the compressor, in typical XL multi-stage compressor of the gas turbine engine, the velocity usually are changed approximately to the 20% along the multi-stage compressor. But density could be changed at 4-5 times. So in any case, density will make the greater influence to the working process than the normal velocity. That's why we could to make such assumption. And if in real compressors velocity velocity are changed, it will have no great influence to the final results. So, okay, let's apply this equation to the compressor. What we have in the compressor? In the compressor, we are increasing pressure. The main aim of the compressor of the gas turbine engine, increasing pressure. And finally, it leads to increasing density. By other word, rho 2 more than rho 1. And if we apply this knowledge to this equation, we could to remove these velocities, we will find what the relationship between F1 and F2 more than 1. So this value more than 1 because the density in the compressor are increased. So what it means? It means what the cross-section area in the inlet of the compressor will be more than cross-section area at the outlet of the compressor. And finally, it leads what the blade height will be reduced from the inlet to the outlet. So, and here you see typical high pressure compressor. This is high pressure compressor of the engine Rolls-Royce Pegasus. You see high blade height at the inlet and the small blade height at the outlet. It's not clearly seen. Let's remove. So you see the same in the centrifugal compressor. In the inlet you have high blades. At the outlet you have small blades. So using continuity equation, we are explain what the blade heights in the compressors must be reduced from inlet to the outlet. The main reason of reducing of the blade's height, increasing density. Because you are increasing density, your mass of your fluid became to have small volume. And to avoid losses, to avoid reducing pressure, you need to reduce cross-section area, and you need to reduce blade height. So, in my opinion, it's very interesting conclusion because it's explained why the compressor looks like we know. So, you see the typical compressor and you see what the blades height are reduced from inlet to the outlet. So, and now we are explain why it's happened. In my opinion, it's very interesting. So what else? And I want to pay your attention. Very often when I ask the students in the exam why the pressure are increasing the compressor, uh, the students says what because blade heights are reduced from inlet to the outlet, blah blah blah, and finally increase pressure. It's not true. Increasing pressure, it's not the result of reducing of the blade height. First, you are increasing density, and after that, to avoid reducing density, to avoid losses, you need to decrease cross-section area, you need to decrease blade height. That's why reducing of the blade height in the compressor, it is not reason of increasing pressure. It's the conclusion from increasing pressure. It's unfortunately it's the typical mistake for the students. So, and let's apply this equation to the turbine. In the turbine, density will be decreased. And we could to say, finally, we could to say what the relationship between the F1 and F2 will be less than 1. And it's mean what the F1 cross-section area at the inlet must be less than cross-section area at the outlet. And it's mean what the blade height of the turbine will be increased from inlet to the outlet. So here you see the example of the flow path of the low pressure turbine. You see in the inlet small blades, at the outlet high blades, and you see what the blade heights at this turbine will be increased from inlet to the outlet. In my opinion, it's very interesting conclusion because it's explained why the turbine looks like we know. It's very conclusion, and if you look to the different type of the gas turbine engine, for example, here simple turbojet engine, here turbofan engine, here small engine with centrifugal compressor. In any case, you will see the same picture. In the compressor, in the inlet, you have the long blades. At the outlet, you have short blades. Here, the same long blades, here small blades at the outlet of the compressor. In the turbine, the opposite picture. Small blades at the inlet, long blades at the outlet. And at this turbine, the same. Very small blades here, very long blades here. So, these conclusions are common for all type of the engines, for all type of the turbomachinery, and I think it's very interesting because this equation explains why the compressor and the turbine looks like we know. So I think that's all about the application of continuity equation to the. I hope you remember the classical shape of continuity equation. The classical shape of the continuity equation, it's the mass flow rate equal to the density, to the normal velocity, to the cross-section area. But using this equation are not convenient because you need to know the density. But I hope you are remember what the density could be calculated using Mendeleev-Clapeyron equation like this, and you see what at this equation, here pressure, here density. For calculating of the density, you need to know static temperature and static pressure. Usually we doesn't know this information. Typically from the test, typically from the thermodynamic calculation, we know total parameters. I refresh to you the information from the previous lectures, what we are used the top star to designate total parameters. So typically, we know total parameters from the thermodynamic calculation from the tests. But for the calculating of the density, we need to know static parameters, and we doesn't know it. That's why using gas dynamic function, using Mendeleev-Clapeyron equation, we could transform this equation to such shape. So it's not very complex, and I hope if you want, you could to repeat this transformation. But finally, we are receive this equation, which are called continuity equation sorry, in stagnated parameters or in the total parameters. One second. Sorry. So these equations are more convenient for the real practice for calculating of the gas turbine engine and for calculating of the turbomachinery, because typically we know total parameters. What we have at this equation: G, mass flow rate, M, this value. This is constant value which depend from the properties of the fluid. You see what inside the formula for the N, you see only adiabatic index and gas constant value. All these parameters depend from the fluid properties. That's why M is the constant value which depend from the fluid properties. So F, cross-section area, total pressure, total temperature, and Q from lambda. This is gas dynamic function, and this is angle between the flow direction and the normal direction. These equations are very widely used in real practice. For example, I could to show to you some example of using this equation. Example number one. You have the compressor, and you know all parameters in the inlet. You know total pressure, this one. You know total temperature in the inlet section, this one. You know mass flow rate through the inlet. You know hub diameter, this one. You know shroud diameter. What else? You know alpha, 90 degrees, this one. And you need to find the static parameters at the inlet of this compressor. How to calculate it? Very easy. We need to use continuity equation. So let's a little bit erase. So let's look carefully to this equation. Mass flow rate. We know mass flow rate. This value, we know this value because we know the air, what our working fluid is air, and of course we know air properties. Total pressure, we know it. Where is it? This one. Total temperature, we know it. This one. Alpha, we know alpha 90 degrees, it's mean what sinus alpha leads to the 1. We doesn't know at this equation only two things. We doesn't know cross-section area, and we doesn't know Q from lambda. Could we find the cross-section area? Yes, of course. We know the inlet and we know hub and shroud diameter of the inlet section. That's why we could to calculate area of inlet cross-section using such way. P 3.14 divided to 4 D shroud at second degree minus D hub at second degree. So using this way, we are find cross-section area. And if we look carefully to this equation, we don't know only Q from lambda. We are extract Q from lambda from the continuity equation. And finally, based to the parameters which we are already know, we are calculate the Q from lambda. What it's give for us? If we know Q from lambda, it's the gas dynamic function, you could find using equations, you could find using tables values of P from lambda and value tau from lambda. And we could find, okay, let's find this value. I refresh to you what the P from lambda, it's the static pressure divided by total pressure. Tau from lambda, it's the static temperature divided to the total temperature. And based to this equation, we could find static parameters. P1 equal to P from lambda multiplying to the P1 total, and the same equation for the temperature. About the density, very easy, we will use the Mendeleev-Clapeyron equation. Like this. So the tasks are complete, and we are find static pressure, static temperature, and density. The second example, much easy. So we know approximately the same way like in previous case. So we have the compressor, and for inlet section we know hub diameter, we know shroud diameter, we know total pressure, we know total temperature, we know velocity, and that's all. And we know what the direction normal to the inlet section, it's mean alpha 1 equal to 90 degrees. So our aim to calculate mass flow rate. Of course, we have continuity equation which could to help to ask mass flow rate. And let's look carefully to this equation. We need to calculate mass flow rate, and okay, we will not change this equation. So m, we know value of m, it's depend from the properties of the fluid. About cross-section area F, we will calculate it like in the previous case, like annular, like area of annular channel. D shroud at the second degree minus D hub at the second degree. Pressure, we know it, this one. Temperature, we know it, this one. Q from sinus alpha leads to 1 because alpha 1 equal to 90 degrees, and we doesn't know this value. How to calculate it? We need to calculate value of lambda based to the velocity, C1 divided to adiabatic index divided K plus 1, gas constant value, and total temperature. So, based to this equation, you could to calculate lambda, and after that, using gas dynamic function, you are find Q from lambda. So, and after put Q from lambda to this equation, and you could to calculate mass flow rate. So you see what it's very typical example, and you see what this equation have very wide application. So in any case, you could to imagine a lot of tasks. For example, at one task you need to calculate mass flow rate. At the second task you need to calculate sizes. In other task you need to calculate what else? You need to calculate velocity and other parameters. That's why these equations are very useful for calculating of the turbomachinery. So let's skip the example number 3. It's approximately the same like a previous two, but it's rather big example, and it's not convenient for me to write formulas using mouse, and that's why let's skip it. So guys, that's all about the continuity equation. And let's discuss the energy equation. So in the turbomachinery theory, we will use 4 energy equation. It will be energy equation in mechanical form, in absolute motion, and in relative motion. And energy equation in heat form, in absolute and relative motion. We will study 4 energy equation. Most of this equation you are already study in gas dynamic courses, or maybe in during physics courses. I refresh the information about receiving this equation from one hand, and of course for us it will be much interesting to apply this equation to the turbomachinery and find some conclusions which will help to us to better understand the working process of the turbomachinery. So today we will discuss the first energy equation. It will be energy equation in mechanical form in absolute motion. By other words, this equation have name Bernoulli equation, and I hope you are know this name, you are know this equation, and you are already study this equation. That's why I'm only refresh how to receive this equation, and we will discuss some important conclusion from this equation. Conclusions deal with the turbomachinery, of course. So let's study the flow through the random turbomachinery. At this case, it's not important what kind of the turbomachinery, what kind of the blade row. Is it moving blade row? Is it not moving blade row? Is it axial turbomachinery, centrifugal turbomachinery? At this moment, it's not important. We have random turbomachinery, and we are choosing point O or point 0. It's the random point, which moves along the trajectory S with the absolute velocity c. I hope you remember what the velocity c will be direct in the tangent direction to the trajectory s. Let's make the local coordinate system in the point O. The first xs will be direct along the direction of the particle velocity. So, by other words, it will be direct tangent to the trajectory of the motion at this point. The second x will be normal. Second x will have name n. It will be normal to the first one, and the last one x normal to the previous two x's. So it's very typical approach for the physical tasks, especially for the gas dynamic, when we are creating local coordinate system in the point which we are investigating. So let's take some space around the particle 0, and this space will have the shape of the brick. The size is dl, dn, and ds. Of course, you could to calculate the mass of this brick like volume multiplying to the density, and volume you could to calculate like multiplying dl multiplying to dn multiplying to ds. So we extract this brick around point 0. And to keep this brick in equilibrium, let's replace the action of environment by the action of some forces. What kind of forces are impact to this brick? Three kind of forces. First, it's the pressure forces. Let's look carefully to this brick. We have six walls of this brick, and let's take this wall. The size is dn dl, and we will have action of the pressure P to this side. How to calculate force from the pressure P? Very easy. You need to take the pressure and multiplying to the area of the side to which the pressure will be impacted. You must to multiply to the area. It will be mean dn multiplying to dl. To the opposite side of the brick, you will have approximately the same influence, but in reality, pressure could be changed along the path line. That's why we will have influence of the pressure P plus dp to this wall, and using the same way you could calculate the resulting force which impact to this wall. It will be wall number 2, it will be wall number 1. So the next force, resistance force. Of course, we have some friction, we have some resistance to the movement of our particle, and that's why we have a resistance force. And resistance force are direct in the direction of the particle velocity, but it's direct to the opposite side. So here, this one, you will see resistance force which are direct tangent to the trajectory of the motion and direct to the opposite side of the particle velocity direction. And the last one, last force which through which blades impact to the particle. So by other words, it's the force from the blades. So that's all three kind of the forces. So what I want to say to you, typically the particle moving with some acceleration. That's why we could write the second Newton's law to this brick. The second Newton's law looks like at this picture. It's the vector sum, and it says what the assume of all forces which acting to the extracting volume equal to the mass multiplying to the acceleration. So we are writing the second Newton's law. Of course, it's not convenient to work with the vectors. That's why let's project this equation to the xs, to this direction. After projection, we receive such picture. This is projection of forces from the blades. This is resistance force, and the resistance force are direct along xs, and it's not have any distortion. This is a projection of the pressure forces to the side 1 and side 2. The other sides of the brick have no projection of the pressure force to the xs, and here we have mass multiplying to the acceleration, and velocity c project to the s direction, because it's they have the same direction. So we are multiplying all parts of this equation to the ds and divided by dm, and you see what some elements could be removed. So let's analyze this equation which we are receiving. What we have? The first term, it's the force from the blades, multiplying to the ds to the distance. The force multiplying to the distance, it's the energy, it's the work, it's the mechanical work. That's why at the top part of the first term we have mechanical work, and after that we are divided into the mass. By other words, we are receive specific mechanical work which are supplying from the blades to the flow. The second term looks like the first one, because we have the force we have the force. We are multiplying it to the distance we are receive work. We are divide work by the mass, so that's why we are receive specific work. But at this case, it will be specific work for overcoming losses. The third term, it's the work of the change in pressure. It's the energy which we need to spend during compression process or which we are received during expansion process. And the last term, I hope you understand it, you know it a lot of time during physics courses. It's the changing of the kinetic energy. So, finally, after some conversation, we are received this equation, and this equation is the classic of equation, energy equation in mechanical form in absolute motion. By other words, this equation have the name Bernoulli. This is Bernoulli equation, Bernoulli. Maybe you see other shape of this equation because sometimes to this equation are including energy of gravity forces. But in the turbomachinery, in gas turbine engine, gravity force usually very small are the forces which that's why we will not take it in account. So finally we are receive the energy of equation in mechanical form in absolute motion. And this equation could be called Bernoulli equation. Let's apply this equation to the compressor. So we before we will write this equation to the compression to the compressor. Let's remember how the compressor work. We are supplying some mechanical work to the compressor. We are begin to rotate the rotor of the compressor, and compressor became to create increasing pressure. That's why, based on this information, we could to write Bernoulli equation to the compressor, but the Bernoulli equation for the compressor will be look like the classical shape of this equation. And let's simple try to read this equation based on the knowledge of the working process of the compressor. So let's try to read this equation. Sorry. The mechanical work which you are supplying to the compressor are spent to three directions. First, increasing pressure. The second, to the change of kinetic energy, and the last, to overcome the losses. Sorry. So, in my opinion, it's very important. The mechanical work which we are supplying to the compressor are spent to the three directions. To the increase in pressure, to the change in kinetic energy, and to overcome losses. What's the main aim of the compressor? Of course, if we speak about the gas turbine engine, the main aim of the compressor increasing pressure. That's why our main task during designing process of the compressor to transfer as much as possible of mechanical energy to the first term. So we need to reduce losses, we need to neglectate losses as if it's possible, and we need to reduce changing of kinetic energy. And one additional moment about the compressor. In the compressor, we have two processes which take place together. From one hand, mechanical energy are transferred to the kinetic energy, and from other hand, at the same moment, the kinetic energy transferred transfer to the potential energy of the compressed air. So, okay, let's write the same equation for the turbine. In the turbine, we have extracting of mechanical energy. That's why the sign of the near the mechanical work will have minus. The second moment in the turbine, we have expansion process. That's why the numbers under integral will be changed because we have expansion process. And at the last moment, we need to remember the working process of the turbine, how the turbine are work. We are creating pressure difference between the inlet and expand, and finally we are receive the mechanical energy. Based to this knowledge, we are apply Bernoulli equation to the turbine, and finally we are receive such equation. And like in the first case, let's simply read this equation. We are read step by step every term of this formula. So let's try to read. The energy which we are obtained during expansion process in the turbine are spent to the three directions. First, we are receive mechanical work. The second one, we are change kinetic energy, and we are overcome hydraulical losses. So, in my opinion, it's very important. The energy which we are received during expansion process are spent to the three direction, to the creating of mechanical energy, to the changing kinetic energy, and overcome hydraulical losses. Of course, the main aim of the turbine to creating mechanical energy. That's why our aim, like the designers, to transfer this energy, this as much as possible, reduce loss, and we need to reduce changing of kinetic energy. And like in the case of the compressor, we could say what in the turbine we have two processes which take place together. From one hand, changing of potential energy, expansion of the gases, transfer potential energy of the flow to the kinetic energy, and at the same period, the kinetic energy are transferred to the mechanical energy. So, the next conclusion. Let's take the Bernoulli equation and let's take the definition of the total pressure. And we are, based to this information, we are put this part inside the integral. After some conversation, we are receive such equation. We could to say what is the Bernoulli equation in total parameters. And if we look carefully, we will find what the value of the total pressure will be changed only in the case when the mechanical energy supplying or extracting in your process. It's very important conclusion because it's explain how the total parameters, total pressures will be changed. And if we look carefully to this equation, we will see what the total pressure will be changed only in the case when you are supplying or extracting mechanical energy. Sorry. When you are supplying or extracting mechanical energy. In the case, if you are not supplying mechanical energy, total pressure must be constant. But because we have losses at this formula, in reality, when you are not supplying mechanical energy, total pressure will be a little bit drop because you have losses. So, by other words, in ideal case, if you are not supplying mechanical work, by other words, if you not have moving elements inside your channels, the total pressure in ideal case must be constant. But in reality, of course, we have losses. That's why total pressure in non-moving channels will be a little bit dropped. These physical principles are used for estimate losses in non-moving elements. Such non-moving elements like intake, like nozzle blades, guide vane, combustion chambers, nozzles, tubes, and other elements. If your channel have no moving elements, if your channel have no mechanical energy supplying, the total pressure must be constant in your channel. But of course, in reality, it's a little drop. It's a little bit drop because you have losses, and the value of reducing of the total pressure could be used for the measurement of the losses in non-moving channels. For these cases, I used physical value which have the name total pressure recovery coefficient, and it's equal total pressure at the outlet of the channel divided to the total pressure to the inlet of the channel. In ideal case, sigma total pressure recovery coefficient equal to 1. If you have a huge losses, this value will be leads to the zero. But of course, in reality, we need to create the channels with the minimum losses, and total pressure coefficient must be leads to the zero. And the last conclusion for Bernoulli equation. Let's write Bernoulli equation for very simple case. We are not supplying mechanical energy. We will not take in account losses, and we will think what the density doesn't change. At this case, Bernoulli equation will be looks here, like here. This is very simple shape of the Bernoulli equation. It's really very simple shape, and I think you couldn't use it for solving of the school exercises. But from this very simple equation, we will make, using this very simple equation, we will receive very important conclusion. If you look carefully to this equation, and if you imagine what the velocity will be increased, you will find what the pressure must be reduced, and the opposite picture. What it means? What in isoenergetic flow, in the case then you are not supplying mechanical energy, changing of the pressure and velocity will be opposite. If you are increasing velocity, the pressure will be reduced. If you are reducing velocity, the pressure will be increased. It's very widely used physical principle in modern industry, and the most famous application of this principle is appearance of the lift force on the wing. So I hope you know what the wing have the special shape, and because the wing have such shape, the velocity of the air at the top of the wing more than velocity at the bottom of the wing. So we could to say C1 more than C2. Because C1, the velocity at the top of the wing, more than it's the big velocity. That's why pressure here will be reduced. So, and finally we could to say what the P1 less than P2. That's why we are receiving pressure difference between the top and the bottom side of the wing, And that's why finally we receive resulting lift force, which move aircraft up. Approximately the same physical principles are using in the turbine to the creating the torque. That's why it's very important conclusion. So guys, that's all what I want to say about the Bernoulli equation. I think our time is close to the end. So, do you have any questions?
No, sir, thank you.
Thank you, Prof.
Perfect. Perfect. Okay, guys.
Thank you, Prof.
It's for me. It's very wonder
Thank
to
you,
see
Professor.
to see all you in the Skype. So, guys, thank you for attention. You could to take the record